Right, so welcome to the session on bias and variance. We're going to be taking stuff kind of from the top, and trying to keep like a mathematical formal idea of what's actually happening and how things are defined in mind along the way. Because I know a lot of the time with the AI slides and stuff, they just kind of play around a lot with notation and they um, sort of pull stuff out of thin air. And I'm going to try and not do that too much. And make sure everything's clear about like exactly what different things are. So we're going to start by having a look at random variables, um, and how if you apply like a function to a random variable or you compose a function with a random variable, you get a new random variable. So what a random variable exactly is it's a function from the outcome set to some other set, normally like the real numbers, and it measures stuff you care about. So, for example, if your outcome set is the outputs of a bunch of different, or like all the different ways outcomes from flipping 4 coins, you might have a function that takes this like list of true or false values and counts the number of trues, and that is, the number of heads. And if we then say, okay, but what's half the number of trues? That's like applying a function, like composing this half function with this count function. And so it is also a like random function or like a function of the outcome set. And so it is a random variable. And a lot of the times when we talk about composing functions with random variables, we use a nice little syntactic sugar where we replace like the argument of the function with the name of the random variable. So if you had like count the number of heads and then half it, it might just be half heads. And this means we can like reason about more complicated ideas easily, and we can do more interesting maths around random variables and like properties of our outcomes. And one of those useful things we get from this is expected value. It is takes in some random variable, so a function from our outcome set to, in this case, the real numbers, and it basically and it sums everything up, multiplying by the probability of each output every time. So more likely values are going to have a larger effect on the sum. Less likely values are going to have a going to have less effect on the sum, and it ends up being kind of like the mean, but it's weighted based on the probability of each outcome. And so it's a like neat average. It's like, what can you expect to get from this random variable? Like, what do you expect the total number of heads to be, for example? And it has some nice properties because it's based off sums and integrals, and that is that it can distribute over addition. We'll see this come up in the future, and that you can pull out a constant factor, and that's going to make the algebra and simplification a lot more useful, a lot nicer in the upcoming things. So, like, the point of expected value is it models what do we expect to get? What are we probably gonna get? Like, what should we like guess that we're gonna get before we actually see what's gonna of this random variable from this sample? And yeah, likely values have a bigger influence. Unlikely values should still have effect, especially if they're like extreme. If you've got a die that's like 1, 2, 3, 4, 1,000, the value like if you expect to get a value that's like more than 5, just because even though there's only a 1 in 6 chance of getting 1,000 on this die, it still could come up, right? You're like, if you're playing the lottery, even though the chance that you win like $1 million is really, really low, you can still expect to win like a bit of money because there's still a chance, right? And yeah, if the distribution is uniform, then the expected value should be the mean of the integral of the outputs. And yeah, so the sum or integral weighted by probability meets all these criteria. So In now, we're going to take a little bit of a sideline to supervised learning, and we're going to see how we can develop an idea of like estimators and bias and variance from that. Um, so if we have this like unknown function, it's like f star. It's what we're trying to learn, and it is parameterized by some like unknown functions, so some unknown parameters that are like w star. Our goal in uh, supervised learning is to approximate w star using some input and output examples we've been given. And because we don't know f star, we've also got to choose like a model f, for example, like linear regression or whatever, to use instead. And again, like the actual number of parameters might be different to the number of parameters we're using. So w star isn't exactly like the true underlying parameterization from the literal real world. But it's like the most perfect function, like f star and w star, like the most perfect functions that have the same signature as your model almost. So like f star is like the ideal best linear approximation for the real system, and your goal is to find the w for your given f you choose that is closest to f star, or like that is best and closest. Uh, and because our input values are a random variable over some unknown distribution, each training set is a sample from this random variable. It's like a bunch of IID samples. I mean, not necessarily IID. Well, they're not necessarily independent. They would be identically distributed. So yeah, you take n samples from this unknown distribution that your like real data comes from to get your training set S. And if we use S and F to like calculate W, we like estimate W star, and this estimate for W star is a random variable, right? It's a sort of deterministic function of a random variable S, right? So your learned weights are a random variable. And so an estimator is a rule, according to Wikipedia, it's a rule for calculating an estimate of a given quantity based on some observed data. And so our training process is an estimate for W. It is some process that will estimate W, like guess at W star and try and give its best guess. And we want to know how good our guess is. And because our W is a random variable, we have access to all the tools from probability theory to evaluate how good and how accurate our estimate is. So we're talking a lot about stuff called random estimators. They're pretty simple. They've just got two parts: a true value and a random variable that generates the estimates. So in this case, the true value would be like W star, and the random variable that generates estimates is our training process, our entire like learning process. Like sampling the real world, putting it into some gradient descent, and getting out some like estimate for W star. And from a random estimator, we can calculate its bias. It's pretty simple. It is how far away is our estimate average from the true value. It's the expected value of the random variable part of the estimator, subtract the true value. And again, we're like destructuring here in this notation. And this lines up quite well with how we use the term. So if we're like, oh, this person is like really biased towards a particular towards something, it's going to be like large and positive. So let's have a look at a bit of a work example for calculating the bias for an estimator. In this case, it's like Bernoulli MLE. So maximum likelihood estimation for, again, I've done a video about this before. You can go check it out if you want more information. About like maximum likelihood estimation and maximum a posteriori. But the idea is that we're trying to estimate theta star and find a and find the bias of this estimator. So the expected value of our random variable that like is this learning process, and subtract the actual value. So if we've got a single coin flip, right, that follows this Bernoulli distribution with this unknown parameter theta star, we don't actually care about the order of the outcomes in our training set, because these are like IID, right? If you flip 20 coins, if you get if you like flip 4 coins, if you get heads, tails, tails, and heads, tails, those like the order doesn't matter when you're thinking about like what is the probability of heads or what's the probability of tails. And so we can say that our training set is just a sample from the Bernoulli distribution. It's not Bernoulli, binomial distribution. This might get confusing. It is our training set is entirely characterized by the number of heads. So we can use the binomial distribution from it. It's like n, where it's the number of successes, where the total trials is n, and the probability success is this hidden theta star. So we're trying to estimate theta star, and we have S, which follows this binomial distribution. And so what we do is we like compose this maximum likelihood function. So given some y, the like observed number of heads, what is the theta that maximizes the probability of that a Bernoulli distribution generates y? And so we say, and if we compose this with S, we like sample some training set, like the number of heads from a training set, and we maximize the probability, and so we get this new random variable that is our estimate for theta. And obviously, we'd like to simplify this argmax expression out, and again, expanding out the probability mass function of the binomial distribution is this big complicated guy with like theta to the y and 1 minus theta to the n minus y, and you can find this online. You're gonna have to trust me that the like MLE solution to this, the theta that maximizes NCY theta to the y 1 minus theta to the n minus y is y over n. And that makes sense if you've got like if you flip 10 coins and you get 4 heads, you're like, okay, the most likely outcome, well, the most likely like probability of getting a head is 40%. And so theta MLE is just S divided by n. And that's nice and simple. So if we have a look at its bias, it's going to be the expected value of theta MLE minus theta star, which is again the expected value of and again, so the expected value of theta MLE is just the expected value of S over n, right? Because that's what we saw before, that the maximum likelihood for the probability that maximizes the likelihood of giving a given output is just getting a given number of heads is just the number of heads divided by the total number of coins flipped or whatever. And we can pull that 1 over n factor out the front. And again, you have to trust me on this one, sorry. But like online, you can find that the expected value of the binomial distribution is n times theta star, the like number of trials times the probability of getting a success. And that, again, that makes intuitive sense. You can kind of see why that does work. And there's like proofs online you can look at. And they're not that hard to find, and they're pretty simple. And the 1 over n cancel out. And we can see that the bias of like using MLE to find the Bernoulli parameter is 0. So this AI technique, this machine learning technique, is a very simple machine learning technique, but we can like mathematically prove that it's got no bias. It's always going to be like it's not going to be like weighted away from the true value. However, just because something has no bias doesn't mean it's a perfect estimator. So another way of evaluating how good an estimator is is called variance. It doesn't involve the true value. Um, so normally it's just how spread out is a random variable, and you can think of it as the average distance from the average. So bias is the average's distance from the true value. So like, um, if you've got like 100 different ideas, and you take their average, and it's very far off from the true value, then you've got high bias. If you've got 100 different points and they're all really spread out, then they've got high variance, and that is the expected value of the like distance from the expected value. So inside this expected value expression, we've got like this e of x minus x squared. It's like the Euclidean norm, norm squared, or like mean squared. You can kind of think of this as mean squared error. It's very similar to that. And if you an important fact that we're going to need in a minute, it's pretty easy to prove. Something exercise for the reader is that you can pull out a constant factor from variance, but it gets squared as you pull out. And you just like expand out the squared expression and pull the constant factor out of any expected values that you need to. But what we can do is we can express variance a bit easier as the expected value of x squared minus the expected value of x squared. And this is a pretty simple like exercise in rearranging an algebra, but there is a pretty neat trick where you introduce never mind, I think that's later. Yeah, that's a later thing. So yeah, it's just pretty simple algebra to rearrange to get this maybe neater expression that might be easier for you to remember, or easier for you to calculate. Like if you've already got the expected value, you can square it and then you can subtract it from the expected value of x squared. Like this is sometimes easier to calculate, and it's potentially easier to understand. It's like the average of the magnitude minus the magnitude of the average. So like the second term recenters your spread out like shotgun blast around 0, and so now the first blast, it like disposes of the bias almost. Well, no, that's not quite right. Yeah, it disposes of the bias, and then e of x expected value of the magnitude is like on average how spread it out is it from 0, and then subtracting the magnitude of the average like pulls your shotgun blast back towards the center. Well, and so we can calculate the variance of our maximum likelihood estimation, and so that's again our maximum likelihood estimator is just 1 over n times the binomial, and we can pull that 1 over n out, but it gets squared. And the variance of the binomial distribution, which again, you're going to have to trust me or go look it up for yourself online, I'm sorry, is n times theta star times 1 minus theta star. And so we can see that the variance of the maximum likelihood estimator is 1 over n times theta star times 1 minus theta star. And what does this tell us about Bernoulli NLE? So we can reduce variance by increasing the sample size, right? So if we've got a larger n, that 1 over n factor is going to become a lot smaller. So our variance is going to decrease, and that makes a lot of intuitive sense. If you've got more, if you flip a lot more coins, you're going to be more likely to get a better understanding of what the probability of getting heads is. And so as you do this, flip a bunch of coins, estimate the probability of getting heads, they're going to be less spread out. They're going to be closer together. The other thing is that if you've got more extreme probability, if you've got like 99% chance of getting heads, and you flip heads, your estimated probability of getting heads is going to be very similar, because you're going to get similar results every time, because you're going to get, if you've got like one outcome that's very, very likely, it's going to dominate, and so the results are going to look kind of similar. If that kind of makes sense. Um, so yeah, and these two facts are, one, they make a lot of intuitive sense, but two, we can like deduce them from the equation. We can mathematically have a like analyze the variance of our estimator, and we can learn ways to reduce variance, not but just from the maths. They like appear magically from the mathematics. So uh, the it's very very rare in practice that you're gonna have a low variance low bias model. That's like this sort of mythical unicorn, this like uh best model that you're um that could never really happen. It's like fantasy. Um, so often the time you can have high variance low bias models, or low bias uh high or high bias low variance models. Um, and obviously high bias highest variance, that's a terrible model. You don't want to use it. Just discard. Don't care. But generally underfit models tend to have low variance because when the parameters depend less on the data set, um, they're having a bunch of different data sets isn't gonna the estimate you get isn't gonna be spread out, but they are gonna get high bias because they're just generally gonna be wrong. Uh, you're gonna if you don't have enough degrees of freedom to express your like problem properly, then your model's just gonna be wrong. Um, However, if you've got an overfit model, it means that your parameters, your output parameters, your estimated parameters depend very highly on the training set you give it, which means there's going to be high variance, but generally they're going to otherwise perform pretty well, and so they're going to have low bias. Um, and what Bayesian models do is that they use prior information to reduce variance, but it increases bias because it brings in like prior assumptions. Um, and that sort of often strikes a balance between high variance low bias and low variance high bias. And that's why Bayesian techniques are often useful in practice. And often like a very common example of Bayesian incorporating Bayesian priors, incorporating prior understanding of your model parameters is what's it called? I've forgotten the name. Regularization. That's it. So if you go back and have a look at my maximum likelihood estimation and my maximum a posteriori, sorry to keep plugging this, you should subscribe to Texiland. Is one of the ideas I talked about there and sort of proved is that regularization is an example of using this like prior information. So if you're having an issue with overfitting, you can use regularization to decrease variance, but increase bias slightly, and maybe strike a balance that you're looking for. So one of the important things is that other ways of measuring how good an estimator is, how good a random estimator is, can be expressed in terms of bias and variance. So on this slide, we've got a nice example of how you can use the mean squared error. Take the mean squared error and express it as bias squared plus variance. And again, this is the mean squared error over like entire training sets rather than over entire examples. So you generate a bunch of training sets, or you sample a bunch of training sets, run your learning process on each of those to get this new to estimate your true parameters, and then what's the mean squared difference from the true parameters, like on average how wrong is your model. And there's and this is just some pretty simple algebra, and well, not algebra, just like rearranging and as long as you understand that expected value distributes over addition and you can pull out constant factors, it's kind of like a vector space almost. This is relatively easy. There's one really sneaky trick that we use here, where you add and subtract an expected value of your estimator squared term, and that means that you can use this like -2 something 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 and this like true value squared terms you can take those and package them neatly into a quadratic, um, which lets this like bias squared plus variance idea pop out really cleanly. So yeah, this is just an example of how if you have a different way of measuring how good a random estimator is, or like how effective a random estimator is, you can often express it in terms of bias and variance, and that's often useful for like how do I compare um, how can I compare these two ways of measuring this model, or how can I if you know the variance or if you know the bias, and you know like the mean squared error in this case, you can then work backwards to find the other one you're missing, for example. But there's a couple issues with the stuff we've been talking about, some questions that you might have if you were very skeptical. And one of them is like, how do we calculate the bias? We don't actually know the true parameters. We can't calculate the expected value minus true parameters. However, if we have like a closed form expression, so like an obvious way of getting, or like a determined way of getting the like getting an estimate from the true parameters. So in this case, it's like 1 over n times n theta star or whatever. Like if you can express an estimate or like the expected value in terms of the true value, you can have even if you don't know the true parameters, you can still express the bias in terms of the true parameters. And so if you have, for example, two different models, or yeah, two different models, you can compare their bias just by be like, oh look, this function of the true parameters is always bigger than this function of the true parameters, and so this model has more bias. But again, what if you can't find this like expression of this estimate in terms of the true value? Then yeah, bias just isn't available to you, unfortunately. And to be honest, neither is variance. But instead, we have a sort of simpler approximation of the variance, which is something called the sample variance, and that is the mean squared error between each estimate and the sample mean. So in this case, this theta vector is a bunch of different estimates, and this is their like mean distance from the mean of theta. And so you can still calculate how spread out your examples are, even if you don't have a like formal expression for how spread out any sample would be. And obviously we've been working in one dimension so far, but most models have many parameters. So let's have a look at how bias and variance and expected value generalize to higher dimensions. It's actually really simple. The expected value is just like distributes over vectors, basically. It's component wise. The expected value of a random vector, so that's a vector where like each component is a random variable, or like a random variable that outputs a vector. The expected value of that is just the expected value of each component packaged together into a vector. Very neat, very tidy. And our definition of bias works fine. We can calculate the expected value of a vector, and we can subtract a vector from another vector. That's fine. We don't need to change anything. But because our components of our random vector might not be independent, we need to change the way we define variance to be the covariance of this vector with itself. So what exactly is the covariance? So in the one-dimensional case, it is the expected value of x minus the expected value of y, and times y minus the expected value of x. And it measures how one scalar random vector changes with respect to another. So if you have a look at the diagrams on the left, if the covariance is 0, there's not like a correlation between these two variables, x and y. If it's like greater than 0, then there is a bit of a correlation, but it's still noisy and spread out. And if it's less than 0, then there's also this correlation, but correlation is negative. Like as x increases, y decreases. But again, it's noisy. It's not like a perfect line. And so Uh, to find the covariance of a vector, um, you just uh, take the transpose of the right side and then perform this this like matrix multiplication. Um, so it's like a row on this left half is a column vector and the right half is a row vector, and you perform this matrix multiplication. And otherwise you don't really need to change anything. And this structure of x times y transpose is called the outer product, and it generates a matrix where like the where the square like ij is xi times yj. And this is like the heart and like the core of a lot of O of n squared algorithms. A lot of like O of n squared algorithms can be expressed at some point. They're going to have a outer product in, and so this outer product expression here before is effectively the covariance of every component of x with every component of y, and it's like how much each component varies with respect to every. So the variance of a random vector is how much of does every component of x vary with respect to every other component of x. And if this covariance matrix is diagonal, so that's only numbers on the diagonal, like top left, bottom right, and zeros everywhere else, everything is every component is independent, right? Because there's no there's only a covariance with like x0 and x0 or x1 and x1. They don't influence each other. Yeah, sorry, tangent over about covariance and like outer products. And now we're going to talk about something called bootstrapping, which is how do we approximate epistemic uncertainty from like a small amount of data. And there's a lot of tools like bias and variance. They come into play here. So one of the final ideas that we need to introduce for this is a function called the Dirac delta function. It's not actually a function technically. Don't stress about it. It's like fancy math stuff, and it's basically infinity at 0 and 0 otherwise. It's like an infinitely high spike at 0. And it has a nice special property, which is that it's integral as 1, and that's like it's used a bunch in physics for like to represent like point particles and things. And if we have n samples from an unknown distribution, we can approximate this continuous distribution using the Dirac delta function, with this like average of the Dirac delta function at a bunch of different positions. So this expression is like, if you look at its graph, it's going to be a spike at d0, a spike at d1, a spike at d2, all the way up to like n samples. And if we take the integral of that, it's like the average of the integral of a bunch of these spikes at different positions. And so the integral from like a to b, so the probability, like the estimated probability that your x is in the range a to b, is just the fraction of spikes that are actually caught in that range. And so now we have this approximation for an unknown distribution, and we can approximate this distribution given like only a single training set, only a few samples, and then once we have this approximated distribution, we can generate a bunch more training sets, and on each of these training sets, we can use that as an estimate to estimate like hidden parameters. We can train a model on each training set, and if we assume that our bias is 0, then the true function, the like true value, is going to be equal to the expected value, right? Because it's the bias is the expected value of the like estimated parameters, subtract the true parameters. And so if we assume, or if we like know that our model is unbiased, then we can approximate the true value with just the mean, like the mean of our estimates. because the mean is like a approximation to the expected value. It's an approximation two ways. One, it assumes that the distribution is uniform, because it's just summing a bunch of values up and dividing by and multiplying by 1 over n. It's like assume the probability is 1 over n. And two, like it's approximating using only n examples, right? And because the epistemic uncertainty is the difference between our estimate and like our model that we learn and the true function, that's something that we can people have talked about decomposing like your actual model's error into epistemic and aleatoric uncertainty. Like the epistemic uncertainty is the difference between your model and the true function. And because we now have an approximation for the true function, it's just apply each model to the input and take the mean of the outputs. We can approximate the epistemic uncertainty of our like training process. Yeah, so T of X is the prediction of our trained model. And we take the mean of all the predictions, and that's our like approximation for the true value. And so our approximation for the epistemic uncertainty is T of X minus this mean. What is all the predictions? So that is we generate a bunch of different training examples from our approximation of the underlying distribution that the training samples in real life are drawn from, and we teach a model based on each of those. We train a model on each of those, and then we apply each of those models to X and take the mean of the outputs, and then we subtract that from T of X. Yeah, so the bootstrap models are they're trained on different data sets, and yes, we do just produce them for the estimation of epistemic uncertainty. One of the reasons that you'd want to have a bunch of different models that are similar in this way is that if you're doing something like reinforcement learning or like continuous learning in like a real environment or simulated environment, you can find the input where all these different models will like disagree the most or like agree the least, where they're most conflicted, and that's like a good thing to have a look at and like, okay, let's see what the model thinks about this. Let's give it more examples like this, to like you can identify weak points and uncertainty in your model. So we assume that T of X has the best weights. It has the best weights for the training set that it was generated from. So we approximate the like real world distribution that the training sets are drawn from. We train a bunch of models on each one. Yes, each model in 6 includes T of X. Yeah. So it's like itself and every other one. What happens if the only model is just T of X? There would be no epistemic uncertainty. But obviously that's not really useful. What you'd want to generate a lot of different models, a lot of different training sets, and a lot of different models. Because the epistemic uncertainty is the error that comes from not knowing enough information, not having enough data. If you are using only one bit of data, you're not gonna see the difference between different data sets. Like if I train 2 models on 2 different data sets, even if and they get very different outputs, then clearly there's some kind of epistemic uncertainty. There's probably some kind of epistemic uncertainty in the like model training process, because having different information gives different weights. If we've only got one training set, we approximate the distribution that generated it using this like Dirac delta trick, and then we can generate more, and then we can like see how the model differs, and that's how like that's why we would want to bootstrap this. Is there a similar sentence we can say like 6, but for aleatoric uncertainty too? So aleatoric uncertainty is like in kind of a bit inherent to the data. It's like the difference between your uh output examples and the true real outputs. It's like if you're uh using a like imprecise measuring device, or you're like got like a noisy measuring device, um and that's a lot harder to that's not going to change as you use different data sets. And so uh no, not really. I guess what you could do is you could, because we have like input and output examples that we are generating and training on, we could, and our mean is an estimate for the true value. So you could see the distance between the um this like mean and some output examples that you've been given or that you've generated, but it's not it's not necessarily as relevant, and there are like 4 approximations deep. So yeah, thank you for watching. This is a bit of a mess, but good luck. Goodbye.